In this video, we're going to use the concept of the auxiliary equation, which we introduced in the previous video. We're going to use that now to solve a specific problem. The playlist for all the videos, incidentally, is at the website digito-university.org. Okay, if you watched our introductory video on auxiliary equations, you know the strategy is pretty simple. Here we have a second order derivative. We replace that with m raised to the second power. Then we have plus 3. This is a first order derivative, so we replace that with m to the first power plus 2 times y. There is no derivative here. We can think of that as a differential to the 0 power. So we replace y with m to the 0. Whereas this is just m to the first power. And m to the 0 power, that's just 1. So this is the auxiliary equation. And remember what we did in the previous video, we showed that y equals, say, some constant e to the mx. It can be a solution to this equation provided we know what m is. And now, of course, we can determine what m is just by solving our auxiliary equation. And that's what we'll do here in this video then. So here, of course, we can factor this out. We have m plus 1 times m plus 2 equals 0. So we have two values for m, minus 1 and minus 2. So you can have two different solutions. Let's just start like this, and y equals e to the minus x, m is minus 1. And another solution, y will equal e to the minus 2x. Two different values for m. We have two different solutions here. And whenever we have a second order differential equation, there will always be two different solutions to it. But before we go on, let's make certain that we are really comfortable that, in fact, this is a solution to the equation and that this is a solution to the equation. So let's start here where y equals e to the minus x. Then dy dx that would just be minus e to the minus x, and d squared y dx squared, that will be plus e to the minus x. So we substitute these values into the equation up here. We will have e to the minus x as d squared y dx squared plus 3 times dy dx. But dy dx is a minus sign there, so we'll have minus 3 e to the minus x and plus 2y. But y is this, so we have plus 2e to the minus x. So 2, 3, these cancel, and indeed it equals 0. So this indeed, we've convinced ourselves, is a solution to the equation. Now let's try this one and see if this is also a solution. So let's make some room. minus 2x. So now dy dx that will equal minus 2 e to the minus 2x, and d squared y dx squared, that will equal 4 e to the minus 2x. So we have y, dy dx, and the second derivative. Let's plug these into the original equation. We have d squared y dx squared, that's this, 4 e to the minus 2x. And we have 3 times dy dx. That's this, so that will be minus 6 e to the minus 2x. And we have plus 2 times y, having plus 2 e to the minus 2x. And 2 plus 4, 6 e to the 2x minus 6 e to the minus 2x. Indeed, it equals 0. So what we've done is very straightforward, as you can see. There's no big trick to it, really. We go back to the beginning. Here's the differential equation. Notice all of our coefficients are constants, 2, 3, and 1. So this will work for any kind of differential equation where we have constant coefficients. And right now we're dealing with homogeneous equations where it's equal to 0. If this is equal to some specific value on the other side, we'll deal with that in future videos. We have to obtain a particular solution. But now the strategy is we have a second order derivative, replace that with m to the second power. We have a first order derivative, replace that with m to the first power. A zero order derivative, replace that with m to the 0, which is just 1. So our auxiliary equation is this. Solve it for our values of m, because it's a quadratic equation, so we're going to have 2 values of m. Minus 1 and minus 2, we're going to have 2 solutions. And here they are. Now let's ask this question. If these are solutions to the differential equation, this one works and this one works, what happens if we take a linear combination of these? So let's say we try this. Y equals some constant, say C1, e to the minus x, plus a different constant, C2, e to the minus 2x. Will that work? So let's see. If this is y, dy dx, that will equal, here we will have, this comes down as a negative 1, so we'll have minus C1 e to the minus x. Then here we'll have minus 2 C2 e to the minus 2x. And for the next derivative, the minus comes down and makes this a plus. So we have plus C1 e to the minus x. And here the minus 2 comes down and multiplies this. That is plus 4 C2 e to the minus 2x. So we have y, its first derivative, and its second derivative. Now we we go up to here, here's our equation. We need this. So we have C1 e to the minus x plus 4 C2 e to the minus 2x. And then we have 3 times dy dx. So this will be minus 3c1 e to the minus x minus 6 c2 e to the minus 2x. And then we have plus 2y. Y is this. So we have down here plus 2c1 e to the minus x plus 2c2 e to the minus 2x. So let's see what we have. We have 2c1, 3c1, minus 3c1, all times e to the minus x. So these cancel each other out. And then we have 4c2 plus 2c2, that's 6 times c2, minus 6 times c2, all times this, that indeed equals 0. So what we've seen then, and it's pretty simple to demonstrate obviously, that having this kind of differential equation, it's real simple to write the auxiliary equation, solve the auxiliary equation for m, and then we obtain 2 solutions. And in fact, here we could write the solutions even more general. We could say y1 is some constant, say c1 times e to the minus x, and y2 is some constant c2 times e to the minus 2x. Both of these are solutions, and in fact, if we add them together, that also is a solution to the differential equation. So a second order differential equation will always have two different solutions. In fact, to be precise, we would say a second order differential equation has 2 solutions that are linearly independent. And again, we'll give some more demonstrations of that in other videos when we solve specific problems using the auxiliary equation.